So today I would like to talk about how to calculate fluid force on a surface, and in particular about how to calculate this fluid force from the velocity and pressure fields. So as a topic to focus on, I have this example here. So this is, for instance, the flow through a contraction, and I've drawn a little bit of the flow field here. And the question is, what's the force on the top surface? So this is the kind of engineering quantity we might be interested in. We have a fluid that's creating forces on the top and bottom surfaces. And we'd like to be able to determine what the force is as a function of the parameters of the flow. So what we're going to do is we're going to divide up the surface, and we've chosen a coordinate system for doing the calculations. And we will have done already the flow solution from the microscopic balance, and the microscopic momentum balance would allow us to calculate the pressure field and the velocity field. So this is part of the continuum model that we use to make these kind of calculations for fluids. So we have to divide up these portions and then write the little pieces of area ds in terms of the coordinate system that we've chosen. So this is a complex case, and we would have probably used a computer simulator like COMSOL multiphysics to calculate the pressure and velocity fields. But then we need some kind of way of expressing what the forces are on the surface. So that's the dilemma we have. So how will we calculate the force on the top surface? Well, if we just sort of think in terms of units, if we divide the surface up into little surfaces ds, then if we could do something like take the vector fluid force per area, then area times area, and we would end up with a little piece of vector fluid force for a little piece of area that we've chosen. Okay, so then we have a lot of little vector pieces of vector force, which we can then add up to get the final force on the surface that we're asking about. So by conceiving it this way, we've now identified what we need to obtain, which is this. We need now an expression for the vector fluid force on a little piece of area ds so that we can complete this calculation. So again, I'll remind you that what we know about the flow is the pressure field and the velocity field. And now we need to calculate the stress. And I'm going to tell you how we do that. I'm not deriving everything from the beginning, but I'm showing you what the pieces are, and the derivation is available in other places. So the tool that we use to keep track of how stress is generated in a flow is the stress tensor. So this pi is the stress tensor, and it is a combination of stresses that are due to pressure and stresses that are due to the velocity. The way that the velocity produces stresses is given by the constitutive equation. So this is the Newtonian Constitutive Equation, and you see here that it has the velocity v, which is one of the two fields we already have. And then it has, in addition, one material parameter. This is the viscosity. This is the only material property that we need to get the stress from the pressure field and the velocity field. So now we would just need to be able to interpret this nomenclature. And this is how it looks, for instance, in the rectangular coordinate system. So minus p times I, the identity matrix or the identity tensor, is a matrix, 3x3 matrix that has ones on the diagonal. And so if you multiply it by minus the pressure, you get this expression here. And then we're going to add the viscosity times that del V plus del V transpose that was part of the constitutive equation, which we can just look up in a table from the internet or from most text, any textbook on fluid mechanics. So this is the handout that I use in my class, and the URL is at the top, that has that del V plus del V transpose with the viscosity out front in 3 common coordinate systems that we use in studying fluid mechanics. So this expression has a good number of velocity gradients. But since we know the velocity field, and it'll be a function of some or of at least one of the variables, the spatial variables, since we have the field, we can just take these derivatives. So the act of calculating this stress tensor, this 3x3 matrix, is just taking the pressure field, which we have, and the velocity field, which we have, plugging them in where they go in this equation, adding up term by term to get finally the stress tensor. So that sounds great, although I have sort of left some part of it out. I said if we could have some sort of a vector fluid force per area, multiply it by every little piece of area, and then add them all up, those could sum up to give me the total force. But I haven't really said how we get vector fluid force per area. Instead, I told you that we will have this stress tensor that we can generate from the pressure field and the velocity field. Now I need to tell you the rest of how it becomes this fluid force per area for each individual little piece of area ds, which we'll then add up. All right, so here's pi, and this is how this works. We have a little piece of area ds that there'll be a series of them that we're going to add up at the end of the day. And these areas have unit normal, which I'll call n. Okay, so n is the unit normal of the ds. So to get fluid force per area at the location where this is the ds and this is the unit normal n, we have to dot that unit normal with the stress tensor. So we're going to add these up at all different locations on the surface on which we're calculating the overall force. And so we're going to have to evaluate this at the surface. And this becomes this part right here. So this is this. So we take this fluid force per area, we multiply it by the area, and we add them up, which is the same as integrating to get the total force. These integral signs are really elongated s's. Think of them as summing. So we're summing over all the ds's until we get the entire domain, the entire surface we're thinking about covered. So that's that surface capital S. So here's the answer to the question that I posed. Where do we get the force per area? How do we translate the pressure field and the velocity field into the force on a surface? And the answer is we take the velocity field and the pressure field and generate the stress tensor pi. And then we have to identify little differential pieces of area and their unit normals, and then carry out the integral to get the total force. So that's the general idea of what we're doing. Let's get a little specific now so that we understand what we're doing. And I have a short example, very simple, that I'd like to do. And then I'll do another video as a follow-up with a slightly more complicated example. All right, so this is the classic simple flow that Newton used in deducing Newton's law of viscosity, which is a simple version of the Newtonian Constitutive Equation. And we can use the Navier-Stokes, which is the microscopic momentum balance, to calculate the pressure field and the velocity field for this flow. So I'm not doing that, but these are the answers. The pressure is uniform and constant in all locations. And the velocity field, for the coordinate system I've chosen, there's no flow in the x, there's no flow in the y and the z direction. Velocity field is this simple function of the distance y. So as we pointed out in the earlier discussion, we need to first calculate the stress tensor. And so each one of these p's becomes p naught because p is equal to p naught. So I can just sneak a naught on there and say, okay, that one becomes p naught. And then I have to carry out the derivatives here. So I had the velocity was equal to 0, 0, v over h y in this coordinate system. So this means everywhere I see a vx, that velocity component is 0. And then everywhere I see a vy, that velocity component is 0. And then the vz velocity components are not 0, but they're not a function of all the variables. They're only a function of y. So dv z dx, right? So vz is equal to v over h y. The partial derivative with respect to x is 0. The partial derivative with respect to z is also 0. And we end up with only one non-zero derivative to keep in this whole expression. And so this is equal to the derivative of this with respect to y, which is just dvz dy is equal to v over h. So now we'll just recopy this onto the next sheet. Don't forget the viscosity. If you check the units of your calculations, you can often find when you've done something like forgotten to write the viscosity. All right, so I'm going to now do the calculation of the force on the surface. All right, so I'm going to remind myself what that is. It's the integral of n dot pi at the surface ds equals f. Let's go back and take a look at the geometry so that we can identify ds. So this is the surface we're asking about the force. So we're going to draw a little square in sort of 3D here. This is a xz plane. So this ds is equal to dx dz. Okay, so this is an xz plane. So ds is dx dz. X goes from 0 to the width, 0 to w, and z goes from 0 to L to span the entire extent of the top. The other thing we need is to know what the unit normal is. And I said it was the unit normal to ds. So it looks like it might be this upwardly pointing unit normal. But remember, the top of this cell is not even in the fluid. We're doing a calculation based on the velocity and pressure field in the fluid. So the surface that we're asking about, where the fluid action creates a force, is the wet surface, which is underneath here. So it's actually a downwardly pointing unit normal that's exactly in the minus y direction. So n is equal to minus ey, or ex, ey, ez, a vector 0, minus 1, 0. The last piece of thing to ask ourselves is what this at the surface means. And at the surface means we need to be able to identify where this surface is in the expression for n dot pi. And this is a surface that's at position y equals h. So we've chosen a coordinate system that works really nicely, the rectangular coordinate system, with the shape of our flow domain, and that's why it's turning out so nicely. It actually turns out that we don't need to, there are no y's left over after we calculate n dot pi, but nevertheless, this is a good exercise to understand what this at the surface means. All right, so let's carry out this little integral. So n was 0, minus 1, 0. And pi, okay, pi is this. And so there's going to be minus p naughts down the diagonal. We add those to whatever else is there. And then these are 0, 0, 0, 0. So these are 0. This one is the 0, and so is that one. And the only one that's non-zero are these two terms here, which are just equal to mu v over h. V is the velocity that the upper plate is being pulled at. So that's now become a matrix calculation. This is n dot pi. And at the surface means if there were any y's in here, I would have to set all the y's to be h. But it turns out everything's a constant, so nothing actually changes. All right, so this is a 1 by 3 and a 3 by 3, and the result will be a 1 by 3. So now it's 0 times p naught plus 0 times minus 1 plus 0 times 0 is 0. 0 times 0 plus minus 1 times minus p naught, which is p naught, plus 0 times this, which is adds nothing. And then the third one, 0 times 0 minus 1 times mu v over h plus 0 times p naught. And so there's our final answer. Let me tidy that up a bit. My minus sign looks a little confusing. So it's minus mu v over h. These are all written in the x, y, z coordinate system. It's my habit to write this just to make sure, since I know that quite often I will be using coordinate systems other than the rectangular coordinate system, for instance, the cylindrical or the spherical coordinate system. So I want to know which coordinate system I'm referring to. All right, so this is n dot pi at the surface. ds, we said, was dx dz. It's an xz plane. And we have the limits. So we have f equals the limits, the integral of, I'm going to switch this to be a vertical vector because I'm just going to be integrating each term separately. 0 p naught minus mu v over h, x, y, z, dx dz. X goes from 0 to w. Z goes from 0 to L. And I have the integral that I need to get my final vector force on the top surface. Now this is actually all a bunch of constants. So this is a particularly easy problem that I did. So it's 3 integrals. It's the integral of 0 dx dz, which is 0. It's the integral of p naught dx dz, which is p naught lw. And it's the integral of this constant dx dz, which is this constant times L and W. So F equals, I can just move the constant vector out, 0 p naught minus mu v over h, the integral from 0 to L, 0 to W of dx dz. And these just give me L and W, and I get 0 p naught LW minus mu v LW over h. So this is a vector that in the z direction has a force that is the force on the liquid that is a result of this moving boundary. In the y direction, it has pressure, the uniform pressure times the area of the plate. That's a normal force. So that's the normal force that you would expect because it's at atmospheric pressure. And there is no force in the X direction. There's no tendency to go sideways. So that's what I wanted to show you. I'll do another video right away to do laminar flow, which is a little bit more complicated, and that'll be more practice for being able to calculate the forces on a fluid on the surface when their fluid is flowing present. So look out for that other video.